Now in this topic we are going to study how to locate the roots of a quadratic equation. That means without actually plotting the graph of the quadratic equation or without actually calculating the roots, we just want to know the location of roots based on various conditions, as we will see later. So here is our standard quadratic equation, which is ax square plus bx plus c. Here we know that a, b and c are the real numbers and a is non-zero. Now we know that the formula for x is given by x is equal to minus b plus or minus square root of discriminant, let's denote it by just delta here, whole divided by 2a. And we know that delta is nothing but b square minus 4ac. So we already know this particular fundamental formula to calculate x. Now based on plus and minus, we will get two different roots. Let's denote them as alpha and beta, and for the sake of convenience, let alpha be the smaller root. So in all the discussion in this topic, we will assume that alpha is the smaller root and beta is the bigger root wherever they are distinct. Now here the main idea before we study the various cases is to note that suppose let us see a particular graph of a quadratic expression. Now here the minimum point of this particular quadratic expression will be obtained when x is equal to minus b upon 2a. So which comes from basically this particular portion. That is, when we ignore the delta, we are left with minus b upon 2a. So that's where it has the minimum value of the quadratic expression. Now here it does not matter whether we are talking about delta is positive, negative or 0, because that will give rise to the already known cases, that is the distinct two roots or the two equal roots or no real roots. So that does not matter here. What we want to first understand is that whenever x is equal to minus b upon 2a, it will have either the maximum or minimum value of the given quadratic expression based on whether the graph of the quadratic expression opens upwards or downwards based on the value of a, as we know. So in all of these cases as shown here, we will see that the value of x where we get the minimum or maximum, that is nothing but minus b upon 2a. So this we have to keep in mind as we study the further various cases of locating the different roots of quadratic equation. So now let's move ahead and see the first case. Now here it's given that alpha and beta are greater than certain constant, certain number k. So we want to develop what is a condition whereby we will say that alpha and beta are greater than k. Now here let us see the two broad cases first, that is what happens when a is greater than 0 and what happens when a is less than 0. Now we know that when a is greater than 0, the graph is going to open upwards, the parabolic shape is going to open upwards, and we can get either this particular case or we can get this particular case depending on whether delta is positive or delta is 0. So it does not matter here whether we consider greater than 0 or less than 0, because as we will see the conditions turn out to be the same. So let us denote the two roots as alpha and beta, and now since we want alpha and beta to be greater than k, it means that k must be located somewhere to the left of the smaller root alpha. So now here we want to develop the condition. Now we observe that if we consider the f of k, that is the value of expression when you put x equal to k, here f of k will be definitely positive as it's clear from the picture. But if we just say that f of k is positive, then it may include some region here also, because there is some k here which may have the positive value of its function. So that means we have to somehow restrict that. So for that, what do we do is, let's consider this mid value which we know that it occurs when x is equal to minus b upon 2a. So now here let us develop the requirements. That is, if we want two distinct roots, then the first condition is obviously the discriminant has to be positive. Then we know that here the parabola is opening upwards, so we want a to be positive, and we also want f of k to be positive, because as we have seen, k is to the left of the smaller of the two roots, but then it can be on the other side of beta. So to avoid that, we must put the restriction on k, that k has to be less than minus b upon 2a. Alright, so here we have these particular set of restrictions. Now you will see that even the same set of restrictions applies whenever we have delta equal to 0. So the only difference it creates because of delta equal to 0 is that the roots are equal, but the rest of the conditions are exactly same. So that is the first case, that is the first possibility when alpha is greater than 0. Now let's see what happens when alpha is less than 0. So here also let us see the first condition, that delta is greater than 0. So here we have delta greater than 0. Then we have a less than 0, therefore the parabola is opening downwards. Now let's denote the roots alpha and beta, that's where the graph cuts the x-axis. Now once again, if you want alpha and beta to be bigger than the certain number k, then k must once again appear to the left of alpha. And here we see that for this particular situation, f of k is now obviously negative, and we of course must have k less than minus b upon 2a. Because otherwise it may have any other value of k in this particular region also, which is what we don't want. So now let us try to somehow merge the conditions so that we can write a single set of conditions for both of these cases. So let us see how we can do that. We observe that in both of the cases, since basically we want the roots, so we will say that delta is greater than 0 is definitely required. Now if you observe the conditions for a and f of k, in the first case we have both of them to be positive, whereas in the second particular case we want both of them to be negative. So stating these two conditions differently can also be done in a single condition, that is, the product of a and f of k has to be positive, because when either both are positive or both are negative, we can effectively say that product of both of them has to be positive. So therefore let us write down that condition as product of a and f of k has to be positive. And lastly, if you observe the last condition, that is, we see that k has to be less than the minus b by 2a. So that is also common in both of them. So we have the third condition, that k should be less than minus b by 2a. So this is the final set of conditions for the two roots to be greater than some number k. And it is applicable in the other way also, that is, if we are given that these particular conditions are present, then we can deduce that the two roots are greater than that number k. So this is how we develop the conditions for location of roots. Now let's go ahead and see the next type of situation. Now here the two roots are required to be less than k. So once again, let us consider the two cases as in the previous situation. We'll see that there is just one change in the requirements, otherwise mostly everything is similar. Now here we want two roots less than k, so k will come obviously to the right side of the bigger root, and here also you will see that f of k is greater than 0, then this particular value is nothing but minus b upon 2a. So now here we have a is positive, delta is also positive. I think I would better write delta on top because that is anyways required to have the roots. Then we want f of k also to be positive, and lastly we want k to be greater than minus b by 2a. So this is the set of conditions for two roots to be less than k when a is greater than 0. Now here once if we consider the other possibility, that is when a is less than 0, we know that the parabola will open downwards. The two roots are alpha and beta. Here the value is k. Now here we see that the value of f of k will be negative, and here is the value of x, which is minus b by 2a. So once again we have delta greater than 0 to have some roots. Then we are talking about a less than 0, and here we observe that f of k also is less than 0 and k is greater than minus b by 2a. So now let us merge these both sets into a single final set. As we know, we can see that delta has to be greater than 0 to have two roots. Then once again if you observe, in the first case both of a and f of k are positive, whereas in the second case both of a and f of k are negative. So we can merge them into a single condition and say that the product of a and f of k must be positive. So that is where we have the second condition. And the only change from the previous situation is that now here k has to be greater than minus b by 2a, which was less in the previous situation. So this is the final set of conditions for the two roots of the quadratic equation to be less than certain constant k. Now let's move ahead to the third possibility. Now here it's given that alpha is less than k, which in turn is less than beta. So that means the given constant k lies between the two roots. Now let us see what is the possibility for that. So once again we start off with a greater than 0 and a less than 0. Now here we must have specifically the distinct roots, otherwise if the two roots are equal then the k has to be same as that. So let's denote this as alpha and beta. Once again we have delta greater than 0, then a also greater than 0 if it is opening upwards. Now let's denote somewhere some arbitrary position of k. Now here we will observe that f of k turns to be negative, because since it lies between the roots, if parabola is opening upwards, then any point which lies between the roots will have its function in the negative direction. So we have the condition as f of k less than 0, and if we consider the second possibility, that is when alpha is less than 0, in that case, as we know, the parabola will open downwards. Here we show the two roots alpha and beta. Let's show k somewhere. Now here it does not matter whether k is to the right side of minus b by 2a or to the left side of minus b by 2a, because we don't need that particular information. So let me not keep that here. You have to just remember that it does not matter here in this particular situation. So once again we show here the f of k, and as it's seen here, the f of k is positive when the parabola is opening downwards. So once again, to write the conditions, delta should be greater than 0 here we are having the case of a less than 0, but now f of k is greater than 0. So now if we merge these both sets, we have the final set of conditions as delta greater than 0. Now let's observe here, when a is positive, f of k is negative, and whereas in the second case when a is negative, f of k is positive. So basically they are of opposite signs. So in other words, it means if we take the product of them, that will be a negative. So therefore we have f of k into a, the product has to be negative. So this is the only condition, the two conditions for certain number k to lie between the two roots alpha and beta. Now let's go ahead and see the next condition. Now here we are given that alpha and beta lie between certain interval k1 to k2. So we want to develop what is the condition for this particular situation. So let's again have two cases, a greater than 0 and a less than 0. Now here we have the two roots alpha and beta. Now when alpha and beta are contained between an interval or within an interval k1 and k2, so k1 must be to the left of alpha and k2 must be to the right of beta, so showing their respective values of the functions. Now here once again we have the basic condition that delta should be positive to have the two roots. Then we observe that both of f of k1 and f of k2, both of these are positive. And if we just say that both of these two are positive, then we won't be able to distinguish whether k1 and k2 are on the two different sides of alpha and beta, because we may have somewhere k2 here also k2 function is positive, but we want to avoid that. So therefore we must put an additional restriction that minus b upon 2a, as we know this number must lie between k1 and k2. So therefore let us put that additional restriction that k1 has to be less than minus b by 2a less than k2, and we of course have a greater than 0 because it's a parabola opening, of course. Now let us see what happens when we have the other case, that is when a is less than 0. Once again we show the two roots alpha and beta. We have k1 and k2, then minus b upon 2a. Now as we know here f of k1 as well as f of k2 will be negative. So let's write the set of conditions once again here. Delta is positive, a is negative, then f of k1 is negative as well as f of k2 is also negative, and once again we must have k1 less than minus b by 2a, which in turn should be less than k2. So this is the final set of conditions. Now if you want to merge them into a single set, so we see that first is the condition that delta should be greater than 0. Now if we look at these three conditions, that is a, f of k1, f of k2, all of these should be positive in the first case, whereas all of them should be negative in the second possibility. So let's take two pairwise products and let us write it as the product of a into f of k1 has to be positive and similarly the second product, that is a into f of k2, has also to be positive. So which takes care of both of these possibilities. And the last condition is exactly identical in both of them, which is k1 should be less than minus b by 2a, which in turn should be less than k2. So here is the final set of conditions for the two roots to lie between any specified interval k1 to k2. Now moving on. Now here we have exactly the opposite of the previous case. Now here we want some specified interval k1 to k2 to lie between the interval alpha to beta. So in other words, the two numbers k1 and k2 should lie between the numbers or the roots alpha and beta. Alright, so here also let us start with considering the two possibilities. When a is positive, we have vertically opening parabola where we have alpha and beta. Now here we want k1 and k2 to lie between alpha and beta, so let us denote somewhere here is k1 and here k2. Alright, so what do we have here is, firstly delta is positive, a is positive because it's opening upwards. Then we note that f of k1 and f of k2, both of these must be negative because they are in the region between the two roots. And now if we consider, now here also if we see, we don't need to know whether k1 and k2 are to the left or right of the mid value, that is minus b by 2a. So we will not need that particular condition. Let's go to the other case, which is a less than 0, where we have parabola opening downwards. Once again we show two arbitrary numbers between the roots, which are k1 and k2. So here we have delta greater than 0, a is less than 0 here. Similarly we have f of k1 as positive and f of k2 as positive. So these are the conditions. Now merging these two conditions in a final set, we can see that delta has to be positive. Now let's look here. If we consider the pair of a and f of k1, they are of opposite signs. So that means if we take their product, that has to be negative. So therefore we have a into f of k1, that must be negative. And similarly if we see the product of a and f of k2 in both of the cases, so that is where we will note that this product is also required to be negative, whether it's parabola opening upwards or downwards. So we have a into f of k2 to be negative. So this is the set of conditions for certain interval k1 and k2 to lie between the roots. Now let's go ahead to the last situation. Now sometimes it's given that exactly one of the roots of alpha and beta lies in some interval k1 to k2. Now let's see what to do in this particular case. Here we have a greater than 0 or a less than 0. Now let's draw the parabola opening upwards. Here we have alpha and beta. Now let's take that alpha is that root which lies between k1 and k2. So if that is the case, then k1 must be to the left of alpha and k2 must be to the right of alpha, right? So now here if you observe, since it's given that exactly one root lies, so therefore we cannot have k2 anywhere to the right side of beta, because otherwise it would then engulf both of the roots between the interval k1 to k2. So k2 must lie between the roots alpha and beta. So with that, let us now write the conditions for this particular situation. Firstly, we observe that delta should be positive to have two roots. Now here we are having a greater than 0 for parabola opening upwards. Now we note that f of k1 is positive and f of k2 is negative. Alright, now here it does not matter whether it is alpha or beta is the root which is contained in k1 to k2, because even if we consider the other possibility, that is, say k1 is here, then beta is here and k2 is here, still in that case you will observe that f of k1 is negative and f of k2 is positive. So basically the functions at these two endpoints of the interval, they are of the opposite signs. So therefore this particular opposite signs of the two functions will hold in even if we consider the other root. So it is not needed to consider that particular case. Okay, now coming to the second possibility, that is when a is less than 0, we have parabola opening downwards. This is alpha and beta. Let's consider k1 and k2. Now here for k1 the function will be negative and for k2 the function will have positive value. So here we have delta greater than 0, a less than 0, and f of k1, here it's less than 0 and f of k2 is greater than 0. So now if you look here, by merging the two conditions, we definitely want delta to be greater than 0. Now here if we see, in the first case we have f of k1 and k2 of opposite signs, and so is the case in the second situation also, that is when a is less than 0, still we observe that f of k1 and f of k2 to be of opposite signs. So therefore here it's not needed to take into account whether a is positive or negative, because we can have the single condition that product of f of k1 and f of k2 has to be negative. That means they are of opposite signs. So definitely one of the roots will be contained between k1 and k2. So this is the only set of conditions for exactly one root to be contained in the interval k1 to k2. Now let us see some of the examples based on these conditions for the location of roots of a quadratic equation.